All right, cool. I think we're good to go. All right, so good afternoon. How is everybody today?
Okay.
Good.
Question mark?
All right, let's start with homework questions. I haven't been on Discord in a few days. Can you re-ask your question here? Or I can hop on Discord, depending on how many messages there are.
Can you go over set builder notation again?
Sure thing.
After Garrett or whoever.
All right, let's see. On homework 1, number 2 asks to list the elements of the set. So in section C, there would be no elements if I understand correctly, but I don't know if it's more correct to leave it blank or write the 0/. So either way is fine. For an empty set, you can either write curly brackets with nothing in between, or you can write the 0 with a slash through it. They mean exactly the same thing.
Yeah, but it wants us to list the elements, and I didn't know if in set notation would be correct with the empty set, because it's not a set, it's just elements of a set.
Oh, I see. So it's asking for the elements. Yeah, so just say there are no elements.
Okay, just word it out.
Yeah,
Okay.
just word it out. That's always legal. Yeah, because you're right. Technically, the empty set's not an element of that set.
By the way, Nick, your camera is off.
Yeah, I know. I haven't done my hair yet.
Oh.
Yeah, it's important, for discrete structures. All right. Okay, and somebody had another homework question, and I already forgot what you asked. So can you ask it again?
Okay. Just can you go over set builder notation again?
Yeah. Let's see.
I just want to make sure I'm doing it right on section 1.1, number 4. So.
All right. So the general setup for set builder notation is something like this. The set of all x, usually in some universe, such that, and then some condition. So the main thing is, to describe a way in which something belongs to this set, right? So positive is the set of all integers in the set, all elements in the set of integers such that x is bigger than 0, for example. Or the even numbers, would be the set of all integers such that x equals 2 times k for some k that's also an integer. So that would be a way we could describe the set of even numbers using set builder notation. Does that make sense?
Yeah.
Okay.
Can you say such that twice? So like x such that this, such that that, or does that not really work?
So the wording is a little loosey goosey. But yeah, the set of all x and z such that x equals 2 times k. Maybe you could say such that. So here's what you could do: the set of all x and z such that there exists a k contained in z such that x equals 2 times k. That would be a valid definition. And when we talk about quantifiers, we'll have symbols for saying things like there exists, and so yeah, we'll definitely see such that's more than once in a proposition or in a set builder notation. And yeah, equivalently, sometimes you see a pipe instead of a colon. take that to mean such that. Like a lot of things, it's context dependent, right? If this is around a number, it's the absolute value. If it's around a vector, it's the length of the vector. If it's around a set, it's the cardinality of the set. If it's in the middle of a statement like this, it means such that. If it's in bash, it's a pipe.
I have another question.
Okay.
On number 4, the set builder, I have t is an element of n, all natural numbers, where n is less than 4. Is that correct notation? Because, like, n is the natural numbers. Can it be less than 4?
So natural numbers, I think in the text, start from 0. So it'd be 0, 1, 2, and 3 in this case.
Right, but I don't have such that n is less than 4. I just have n less than 4. No such that n.
The set of all t and n less than 4. Yeah, put a such.
Less than 4.
Yeah, put a such that in there.
Okay.
Related to that,
Mhm.
the natural numbers, if I wanted to do, like, so for 4b, I have, n contains 0, 1, 2, 3, 4, such that, alpha equals 10 to the n.
Mhm.
Could I technically change the 0, 1, 2, 3, 4, to be a natural number sign instead?
Yeah, if you really mean all numbers from 0, 1, 2, 3, 4 and on up, I think you can use the natural number sign. But like I say, the natural number sign we kind of avoid because it's somewhat ambiguous. Sometimes it includes 0, sometimes not. So if you really mean that, I might do something like the set of all x contained in z, x bigger than or equal to 0. And then you could say and to do some other stuff. Z is the integers.
Positive? No.
No, z is all integers, positive, negative, and 0.
Oh.
That's the set we're going to use most in this course, actually. So that's any integer, positive, negative, or 0. So if you take any integer and you require that it's bigger than or equal to 0, then you've got the positives. You might also see this sometimes, the set of all x bigger than or equal to 0 such that x is an integer. That kind of means the same thing, right? Except that, you know, we don't really know what x's we're talking about, but when we see something greater than 0, we're usually thinking it's a number, right? So this would be the set of all numbers that are positive and are also integers. And that would be the set of positive integers.
Okay, another question. For question 4D, section 1.1, is n contains all real numbers such that n equals 0 a way to write,
Hold on, I gotta pull up the text if you've got a specific. So hold on a second. So which chapter? 1.1?
1.1, number 4,
Okay.
part D.
Part D. Use set builder notation to describe the following sets, and we want a set just containing 0.
Mm-hmm.
That's kind of fun. So what were your thoughts?
I was thinking like a set where n containing all real numbers such that n equals 0.
That's one way to do it. That would certainly qualify. But you could use that, you know, if I wanted to represent the set 17, I could say the set of all real numbers such that x equals 17. Yeah, that's perfectly valid. Just for kicks, could you think of a different way? I mean, the way you did is fine for the homework. So someone did a... Say again?
It wouldn't be an empty list, would it?
No, it's not an empty. So someone in chat said all natural numbers less than 1. So that would work.
What if we use like notation minus notation? So like natural numbers minus positive numbers. Does that work?
We don't have subtraction defined on sets like that.
Gotcha.
Oh no, we do. So if you took the positive numbers and you took away, if you took the natural numbers and you subtracted the positive numbers, yes, that's exactly right. So it's everything that's in here but not in here, and that's exactly just the set 0. So that would be equivalent. You could do the set of all x and z such that x equals negative x. And that would be 0. And in general, there's a lot of ways to specify sets. And any of those are equally as good as any other way. Someone asked, what would 0 be in that case? I'm not sure what that means. Because 0 is just 0. Oh, n take away p. So if n contains all positives plus 0, and then you take away all the positives, you're left with just 0. That's assuming you've tossed 0 into your natural numbers.
Should we define natural numbers before we say something like that?
If you're going to use them, I would definitely define them. But I would say it's probably easier just not to use that. Because then I have to either give you the benefit of the doubt or not give you the benefit of the doubt as to whether you meant to include a 0. So if you want to do something, and say n equals, all integers bigger than or equal to 0, then you can go ahead and use that the rest of your exam or homework.
I have another question, but it's for section 1.2.
Okay.
Number 4, where we're giving examples.
Okay.
Would valid do have our A, B, and C sets be all the same?
No, they can be different from one question to the next.
No, but like for part A of number 4,
Mm-hmm.
if A is a subset of B and B is a subset of C, then A is a subset of C.
Mm-hmm.
Can you technically show that as an example if A, B, and C all are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 or something?
Yeah, so I'd invite you to try to find what we could call interesting examples to illustrate these facts. Some of these facts, if you made all your sets the empty set, these facts are true, but that's possibly not as interesting, right? The goal here is to get some practice dealing with subsets and Cartesian products and subtraction and so on. So try to pick sets that illustrate these things but aren't, doing it in some kind of edge case sort of way. So I would say in general, try to make them different from each other and not empty and not the whole set. And for part D, try to make life easy on yourself. Don't end up trying to take the Cartesian product of sets with 5 or 6 things in them, because you end up writing a lot.
Okay.
Cool. Good questions. Other questions?
Not currently.
Okay. All right. Well, let's move on then. Alright, so let's continue developing set theory. And I want to talk about a few more aspects of set theory, and then I want to talk, probably the last half hour of the class, I want to dig into some of the fun stuff. I want to look at some of the questions around infinite sets and this notion of cardinality. And I'll tell you a story, so that'll be like our story time part of the week. But let's do a few more mechanical things about set theory. So let me introduce the concept of a membership table. And when we have sets, we talked about some identities last time, which ended up looking a lot like Engineering 250 identities. We talked about commutivity and distribution, and we ended up with De Morgan's theorem of all things, and all these facts about how operations on sets relate to other operations. And so we might find, on a homework example or on a midterm perhaps, a question that asks us something like this: prove that if we have a set A and we union it with A intersected with B, we end up with set A. And it sort of makes sense, perhaps, right? Because what do we get in the union? Well, we get everything in A, right, coming from this member. So that's going to give us A right there. But we're also supposed to add in everything that's in A and also in B. Well, anything in this parentheses expression has got to already be in A because it's in the intersection. So we're just going to add things that are already in A into this set. So we can probably believe this is going to end up giving us A. And we could make a Venn diagram where we could see that, this is A, and this is a little section taken out of A. And if we think of those taken together, we get the whole set A. But suppose we want to prove this. And we could do this algebraically, right? We could distribute the union across the intersections. We would get A union A intersected with A union B. And A union A would just be A because we have an identity with that. And we could go on from there, right? But that's hard, right? So we do that in 250 sometimes. But there's an easier way to do this. Now, if you remember in Engineering 250, we had set identities on Boolean operations. We also had truth tables. And you always hope that your teacher, when they asked you to prove something, would say you can use a truth table. Because it's very mechanical, right? You list your variables in all possible combinations, and you just fill out all the columns, and when you're done, you can see that one thing's equal to another thing. Well, we can do the same thing with sets. So we're going to make what's called a membership table. Now we have two sets here, A and B. So I'm going to make a table. I'm going to list A and B. And I'm going to have a series of rows. And each row is going to correspond to a particular situation. So here's what we're going to do. We're going to think of any element in the universe, and there's some implicit universe of elements we can choose from. So if I pick any element from the universe, there's exactly two possibilities. That element might belong to B, or it might not belong to B. Right? But if we're not in some kind of paradoxical situation, right, anything I think of is either in B or it's not in B. So if you're thinking of a set of integers and I pick a pen, right, that's not in your set. If you're thinking of a set of integers and I think of the number 5, that is in your set. So for any element that you pick, just imagine picking one element somewhere from the universe. Could be the number 5, could be a zebra with shoes on, could be whatever, right? For any one element you pick, there's exactly two possibilities. Either it's not in set B, or it is in set B. And I'm going to write a 0 or a 1 under B to indicate each of those cases. So if my element is not in B, right, I'm going to write a 0 here. Well, there's another pair of possibilities since I have two sets. My element might be in set A, or it might not be in set A. And so taken together with the two possibilities for set B, I have a total of 4 possibilities. The first two possibilities, my element is not in A, but it's also not in B, or it is in B. The last two possibilities, my element might belong to A, and again, it might not be in B, or it might be in B. And so these 4 combinations cover all possibilities for any element in the universe as far as its membership in both A and B. All right, well, let's write down some useful facts about this. So let me start a side table. And we'll stick with 2 sets. And let's write down what the membership looks like in the set A union B. Now suppose I have some element I've picked out, and it does not belong to A, and it does not belong to B. Is it in the union? Nope. Alright, suppose I pick some element and it does not belong to A, but it does belong to B. Is it in the union of A and B? Alright, we got 3 yeses for that one. And if it's in A but not in B, same thing, it's going to be in the union. And suppose it's in both A and B, is it in the union? Absolutely. Why? Because this is the set of things that are in A or B. Well, it's in A, so that's enough to be in the union. Alright, what about intersections? Suppose we have an element that's not in A and it's not in B. Is it in both A and B? Of course not. It's not in either of them. Suppose it's in B but not in A. Is it in the intersection? Nope. And similarly, if it's in A but not in B, it's still not in the intersection. But suppose it's in both A and B. Well, that's what it means to say it's in the intersection. It means it's in both A and B. And yeah, this looks just like an or, and this looks just like an and. And let's do one more just for good measure. Let's look at the complement of A. So in this row, I'm thinking of an element that does not belong to A. What's the complement of A? It's everything that doesn't belong to A. Well, I'm thinking of an element that's not in A, so it's going to be in the complement. And here I'm thinking of an element that is in A, and so by definition, it's not in the complement. And so that's what the complement looks like. So this is called a membership table, but it's really just a truth table, right? This is good old 250 truth tables. We basically treat unions as ors, intersections as ands, and complements as complements. So now if we want to prove this identity, it's a rehash of things we've already done. Let's make a column for A intersect B. And we know that's going to look like this. And now we want the union of this column with this column. So 0, 0 gives us a 0, 0, 0 is 0, 1, 0 gives us 1, 1, 1 gives us 1. And now the best part of doing these things, you go back and you look at your columns and you observe that this column is exactly the same as this column. What does that mean? It means that for any element in the universe, that element belongs to this set precisely when it belongs to this set. and it belongs to this set precisely when it belongs to that set. Well, that was our definition of set equality. And so that's totally sufficient to prove that this expression is equal to that expression. So that's how we use a membership table to prove identities. Yeah, yet is a key word for that. Because we can definitely make identities with about 4 sets, and then you got a 4-bit truth table. I probably won't do that to you. All right, any questions about that? All right, let's see. Unions and intersections, we've defined these in terms of 2 sets, but we can define them in terms of more. Oh, left before I could say goodbye. Anyway, goodbye. Have a good weekend. All right, so we know how A union B works, right? We could also define A union B union C as a set of things that are in A and also in B and also in C. And we could define, things that are in A or in B or in C. And we can define the intersection as what I just said, things that are in A, also in B, also in C. And sometimes we want bigger unions and intersections. And so let me do this. If A sub I is a family of sets. By a family of sets, I mean there's a set called A1, there's a set called A2, there's a set called A3, up to some point, right? So maybe I have, A1, A2, all the way up to A10. So I've got 10 sets, but I'm representing them in this way, right? So this is like an array, right? An array of sets, maybe. If I wanted to describe A1, union A2, union A3, union everything up to A10, there's a shorthand way of writing this. We could write something like the union from I equals 1 to 10 of A sub I. And we understand this to be a shorthand for this. And the same thing with intersections. I could describe an intersection of a bunch of sets. And it's a rip-off of summation notation, right? Where we have an index and a lower bounds and an upper bounds. And just like summation notation, the index is irrelevant. I could have used J. I could have used, Q. Doesn't make any difference. It's just saying, let this thing go from 1 to 10 and, do the union of each of those subscriptive sets. All right, let's do an example of that. So let's define a family of sets, A sub I, where A sub I equals, and I'm just going to use dot dot notation, all the integers from I on up. And I'm going to define this to give me a set A1, A2, A3, A4, and so on. So for example, the set A5 is the set 5, 6, 7, 8, 9, 10, and so on. The set A12 is the set of integers starting from 12. Got the idea? A1 is all the positive integers. Alright, so question with this notion of sets, right, where AIs are defined like that, what is the union from I equals 1 to n of A sub I? And when I do questions like this, I like to write out a few sets and just sort of see what it looks like, try to get an idea what the pattern is, and then see if I can convince myself that it's actually true. So suppose n equals 1. If n equals 1, this is just A1, right? It's not even being unioned with anything. If n equals 2, this is a union from I equals 1 to 2 of AI. Well, that is a shorthand for A1 union A2. So what is A1 union A2? A1, absolutely. Right? A1 is the set of integers starting from 1. A2 is the set of integers starting from 2. If I take the union of those, I just get A1. Yeah, funky symbols can be challenging. There's actually a lot of research that, well, there's research that proves everything. But there's research, I believe, that physically taking notes helps you conceptualize and memorize concepts. It's a different modality, it engages different parts of our brains, but it can actually be beneficial to understanding. Whereas I believe that typing on a computer takes you in a very different direction. So I often recommend people actually take physical notes with like pencil and paper. And then especially if you got funky symbols. Alright, if n equals 3, union from I equals 1 to 3 of AI is A1 union A2 union A3. Well, we can write out A3, and that's the set of integers starting from 3. So what's A1 union A2 union A3 equal to? That's also A1. And so for n equals 1, 2, 3, the answer was always A1. And we might hypothesize that, you know, the answer for any n is going to be A1. And then if we think about that, we can probably convince ourselves that's true, legitimately. Because if I start with, if I look at this, this is A1 union with some other stuff. Well, every AI is a subset of A1. Right? Every one of these A sub i's is the same as A1, it just starts further out in the sequence. And so adding any or all of these to A1 is just going to give me A1. And I'm restricting this to only look at where I is a positive integer. But we could define it to start from you know, a negative number also, and that would give us some interesting other issues to think about. But yeah, for simplicity, we're just going to assume that I is bigger than or equal to 1. So there is no A0. Alright, so let's go the other direction. Let's look at the intersection from I equals 1 to n of AI. And remember, AI equals I plus 1. So what do you get when you intersect the first n of these sets? That's not a bad guess for this course in general, but it's not the right answer in this case. AN. What do we think about that? Well, A1 intersected with A2 means find everything that's in common between those two sets. That's going to be exactly A2. If we then intersect with A3 and we find everything that's in common between all three sets, well, we got to throw away the 1 because it's not here. We got to throw away the 2 because it's not here. But all of these things from 3 on up are going to be in all of these other sets. And if we had A4 and we intersected A1, 2, 3, and 4, we would end up with A4. So yeah, this is exactly what we end up with. We end up with A sub n. Alright, so those are playing around with unions and intersections. And we've just established these two facts. We haven't proven them, but, you know, we've waved our hands and come up with a pretty convincing hand wave. Alright, let's try this. What if we take the union of an infinite number of these sets? A1, A2, A3, A95, A1939, A10 gazillion and 5. All of these possible A sub I sets. What if we union them all together? What do you think we're going to end up with? Sorry?
A infinity?
Would we?
It's the lowest number in the set, so it's A sub 1.
Yeah, the union is still going to give us A sub 1. Because any one of these sets that we throw into the union has got stuff that's already in A sub 1. Right? A1 is the biggest set, and these things are all subsets. So this doesn't change. But I think you had an insight on my next question, which is, what if we do the infinite intersection? So we intersect and so this would suggest A infinity. The problem is A is only allowed to be an integer, and infinity is not an integer.
A of all positive number?
So this has to be a single positive integer.
A is approaching infinity?
Possibly. And it doesn't have to be an A, right? I just want to know what this intersection, what the elements of this intersection are. These were nice because they happen to be, you know, things that we could write as A something. But there could be a different answer. Somebody wrote 0, which isn't a set. But I'm feeling like we're close.
Divided by I.
Say again?
Infinity divided by I.
That would be cool. Or e to the pi I.
Infinity plus 1 minus infinity.
That's cool too.
Wouldn't that be infinity minus infinity plus 1? Isn't infinity minus
Yes.
infinity?
Yeah, I don't know.
It's in indeterminate form?
Well, it depends on the day of the week and who you're talking to. But yeah, generally that's an indeterminate form. Alright, so I saw an answer in chat just now. Somebody suggested this. What do we think about that?
But it is populated, right?
Is
So
it?
It can be empty.
Well, let's think about that. So tell me what you think one element of this set might be.
1.
1. So is 1 an element of that set? Well, anything that's an element of the set must be a member of A1 and also a member of A2 and A3 and A4 and A5. Because this is the intersection of them. It's the things that are in all of those sets. And if we look at A2, or if we look at A5, right, that doesn't contain the number 1. So 1 cannot be in that intersection. Right? So 1 is not in that set. And the number 10 cannot be in that set because this includes the intersection with A12, and A12 doesn't contain a 10. So 10 can't be a member of that set either. And it turns out any integer that you think of, right, this big, long, ridiculous integer, well, there's at least one set here that does not contain it. And that's A sub 4376221939. Because that begins with this number and just gets bigger and bigger, but it does not contain this number. So this can't be in the intersection either. And any integer you can think of can't be in this intersection. And since all these sets only contain integers, we must conclude this intersection is the empty set. Truth table, unfortunately, would have an infinite number of columns because we have, potentially an infinite number of sets. But that's an interesting idea. I've never played with an infinite truth table. And that would be an interesting one. Yeah, we are working up to Hilbert's Grand Hotel in a few minutes. So this is playing around with infinities, and infinities can be wonderful and terrible, right? They can surprise us, and they can foil us sometimes, and they can inform us of things. I'd like to point out two things. One, the idea of A infinity is really not that far off, right? A infinity in some sense would, be all the integers starting from infinity, right? I mean, the closest we could get to A infinity would probably be the empty set, right? And, if we just replaced n with infinity, this answer would suggest A infinity, but A infinity doesn't exist. So, over here with unions, we got the same answer when we went to infinity. With intersections, we got to a different answer when we went to infinity. That right there keeps the world spinning, right? That's in some sense the heart of calculus. The fact that unions and intersections on infinite numbers of sets work differently. That's a fundamental property of numbers and sets, and it's the foundation of this thing we call point set topology, which we can specify down to a version of calculus. So there's some kind of deep wisdom hidden in this simple observation, if one searches correctly. All right. Let me toss one more thing out there, which is computer representation of sets. So suppose we have a universe which consists of the letters A, B, C, D, and E. Alright? And we want to deal with sets from this universe inside a computer. Alright, sets are unordered. I'm not going back on that. But for the sake of processing this information in a computer, let's think of these things as having a particular order. So I'm just going to write down, for no particular reason, the 5 elements of my universe in that order. And I'm going to represent any set from this universe with a 5-bit string. And what my bits are going to represent is the values from a membership table that tell me whether each of these elements belongs to my set. So if I wanted to write the set A, B, C, I would write it with this 5-bit number. This one tells me that A belongs to the set, this says B belongs to the set, this says C belongs to the set, and these say D and E don't. If I wanted to write the singleton set D, that would be the number 01000. And with this simple notation, I can store any set of elements from this universe inside a computer using a 5-bit number. So what does the empty set look like? That's all zeros. And what does the universe look like? That's all ones. So this is a useful device. If we're dealing with sets, we can use bit strings to code them internally. And every set corresponds to a bit string, and every bit string corresponds to a set. And it's a one-to-one correspondence. But yeah, you do have to specify the order so you know that this means an A as opposed to, you know, a B or an E. And how many possible 5-bit strings are there? How many different ways can I write 5 bits? Two to the 5th. And since each 5-bit number, each 5-bit string corresponds to a set, I have 2 to the 5th possible subsets of this original set. So this is another version of this idea that the number of things in the power set of S is equal to 2 raised to the number of things in S. And we can get that just by thinking about representing these things with this binary notation and using what we know about the number of bit strings with n bits. So there's a second visitation of that fact. All right, good so far?
Sure.
All right, so on to story time. So you don't need to take notes on this. So one of the things I like about this course is that, you know, as I said in the beginning, we start with things that we understand, like sets or counting or stuff like that, and we sometimes build up to very, very strange consequences of these simple ideas. And I think that makes the subject intriguing. I think it makes the course fun. So, you know, we're on schedule so far for the quarter. It's been 3 classes and we haven't fallen horribly behind yet. So sometimes on Fridays I'll try to put out some of this stranger stuff that pops up in the subject. So so we're gonna do a bit of story time here, and this is not on the exam, right? But it's interesting stuff. So I'm going to tell you a story, and I'm going to start with some historical facts, and then we'll deviate into the fiction part after that. So the historical part relates to a mathematician named David Hilbert. And if you study math, you know Hilbert's name. He was a mathematician who trained, you know, a number of students. And at the end of the 1900s, he posed a series of problems. And he suggested that these would be interesting problems for the math community to work on for the next 100 years. So he sort of put down, you know, his own vision of a roadmap for guiding the development of mathematics. And these, you know, were subsequently called Hilbert's problems. And you see, you know, headlines now and then about, you know, progress on Hilbert's 23rd problem, or a solution to Hilbert's 12th problem. And so David Hilbert was, you know, mathematical genius. And you can Google him and you know, find all sorts of interesting things about him. All right, so that's the true part of the story. Now we go into the part that may be fiction, right? So the story goes that David Hilbert, you know, after being very successful in mathematics and so on, he got bored with math, and he decided he wanted to do something different. And he wanted to be around more people, so he said, I'm going to open a hotel. And so he found, you know, a plot of land and an abandoned hotel, and fixed it up and opened it up. And he didn't know anything about the hotel business, you know, but he's David Hilbert, so he's smart, he can figure this stuff out. So, grand opening, Hilbert's Hotel, right? And they open the doors, and it's a mob of people. Everybody from anywhere is like dying to get into Hilbert's Hotel just so they can say, yeah, I spent the night at Hilbert's Hotel, you know. Fantastic success. And his little 12-room hotel is immediately overrun with people who want a room, right? And so most of the people are sent away. So this goes on and happens the next night and the next night, and, you know, after a few weeks, there's, you know, this limitless supply of people who want to stay at Hilbert's Hotel. So what does he do? He expands, right? So he gets some workers, and they add on another wing to the hotel, and now he's got, you know, 50 rooms, and every night the hotel is sold out. And he's thinking, hey, you know, this is a lot easier than mathematics, and I'm making some good money, so I'm going to put some of that money in and make an even bigger hotel. So he expands to 1,000 rooms, right? He builds this big multi-level building, and Hilbert's Hotel now has 1,000 rooms available, and it's still selling out every night. So he adds another building to it, and, you know, he gets some entertainment, and you know, upscales the food buffet, and the hotel just keeps getting bigger and bigger and bigger, and still plenty of demand. Well, this goes on until Hilbert reaches a point where his hotel has an infinite number of rooms. All right? So Hilbert's grand hotel has an infinite number of rooms. Now, what does this mean? Every room in his hotel has a number on the door starting with 1, and all the room numbers are integers. So right next to the front desk is room 1, and next to that is room 2 and room 3, and so on. So if you were to look at the rooms and go down the corridors and go around the corners and move from building to building, you would find this infinite set of doors, each with a consecutive integer on it. Now, there is no door with the number infinity on it, because infinity is not an integer. When we say there's an infinite number of rooms, here's what we mean. If you think of any integer, think of the number, you know, 15,007, somewhere there's a room 15,007, and there's rooms to the right of that. And in fact, there's an infinite number of rooms to the right of that. Okay, so that's what we mean by an infinite number of rooms. Each room has an integer number on the door. But any integer you think of, that's not the last room in the hotel. There's always more with bigger door numbers. Got that idea? Yeah, even if you use Graham's numbers. And if you want to Google large numbers and read the wiki page on that, there's some really good stuff in there. All right, so infinite number of rooms. All right, well, it's getting to be Hilbert's birthday. And people decide they're going to throw a party for him. And they're going to have the party at Hilbert's Grand Hotel. And so invitations start being sent out. And all of his former students, all of his colleagues, anybody who's ever heard about Hilbert, get an invitation to this party. And this invitation blankets the earth. And you know, most of the people on the planet decide, okay, I'm going to come and I'm going to stay at Hilbert's Hotel for his birthday party. And it turns out that there was a team of physicists in Zurich who were working on the multiverse theory and using high-speed particles to try to open up a passageway to a multiverse. And they didn't realize that they had succeeded, because at the moment when their experiment succeeded and they opened up this conduit to a parallel universe, they had just gotten the invitation to Hilbert's birthday. And the physicist who saw it read it aloud. And she said, "Oh, Hilbert's having a birthday party at such and such at this location. We should go." And as she read that out loud, that information was passed to this parallel universe. And in that parallel universe, there were a team of physicists who were doing the same thing, and they passed that information on to another universe. And it turned out there's an infinite number of universes. And everybody in this infinite number of universes heard about this party and decided, hey, we're going to go to Hilbert's party too. And so they all teleported to this universe, and they all traveled to town to try to go to Hilbert's birthday party. All right, so now we have an infinite number of people coming to this hotel with an infinite number of rooms. All right. So these people show up in the parking lot, and it's a big crowd, right? So they have one of these bakery number dispensers that says, please take a number. And as each person arrives, they take a number. And the numbers from this dispenser start with a 1 and a 2 and a 3 and so on. And they get to the front desk, and, you know, I'd like a hotel, and they're like, let me see your number. Well, I've got number 17, and so the person gives them the key to room 17, enjoy your stay, right? And this is, you know, taking a long time, so eventually there's just a pile of keys, and everybody's got a number, and so they just take whatever key is theirs, and they go to their room. And it works perfectly, right? It's an infinite paper dispenser, so it never runs out of tickets. All right, so here's the setup. We have an infinite number of rooms. We have an infinite number of guests. So let me make a set, I'll call it D for doors. So that's the set of doors. And G is the set of guests. And the doors are labeled 1, 2, 3, and so on. And the guests are also labeled 1, 2, 3, and so on. And don't worry about how they get their guest number. It's somehow defined. All right, and so everybody gets a room. The hotel is completely filled now, which had never happened before, right? How do you know it's completely filled? Because if you pick any number on a door, there's somebody in that room. It's the guest with that number. But nobody goes without a room, because whatever your guest number is, there's a door with that number on it also. So the rooms are perfectly filled. All right, you got the setup so far? Grand Hotel, infinite number of rooms, big party, infinite number of people coming for this party. Each person gets their own room. The hotel is completely filled. Every room is occupied. every guest has a room. Sounds great, right? This is a perfect setup for a really awesome party. They have an infinite supply of cake, so, it's gonna be great. But, yeah, so there was one graduate student who was driving in, and their car broke down. And they managed to walk into the nearby town, which was a few miles away, and the mechanic was getting ready to go to Hilbert's party, but said, I've got someone who can fix this for you. It'll take a few hours, and so this poor former grad student is stuck at this garage waiting for their car to get fixed. Well, the car gets repaired finally, and the student drives into town and gets to the hotel. Big party going on now, right? Student walks up to the front desk and says, I'm got here late, but I'm a student of David Hilbert's. I'd really like to stay at the hotel. Is there any way you can fit me in? And the front desk clerk says, yeah, I can do that. Hold on 1 second. And he reaches under the table and he does something, and he comes up with a key, and he hands the person the key and says, here you go, enjoy your stay. And if you already know this story, right, then there's no suspense in here. But the question is, right, how did the front desk clerk manage to fit one more person into a hotel that was already completely filled? And you don't kick anybody out. You're not asking anybody to double up with somebody. You're not building an extra room. So how do you fit one more guest into a hotel that's already completely filled? You could crash on the lobby couch, but they actually got this person a room. And we're not going to go into another universe, although that would be a solution. I've seen the couch where Richard Feynman slept his first night at Cornell, by the way. I've actually sat on that couch because he showed up after hours and couldn't get into his room, so he slept on this little bench in an area. And yeah, so I got one correct answer in private. So yeah, it is an infinite hotel, but every room is filled. Every room has somebody in it already. Infinity plus one is still infinity, but before this person showed up, any room that you picked had somebody in it. And everybody showed up. But this idea that infinity plus one is still infinity, this is pretty close to it. Yeah, put him on the roof. Alright, so here's how you do it. You push a little button under the desk and it lights up a sign in each person's room, and it says, sorry for the inconvenience. Could you please move to one room on your right? And whoever's in room 1 gets up and moves to room 2, and whoever was in room 2 moves to room 3, and whoever was in room 15007 moves over here, and so on. Everybody just moves over one spot, and now room 1 is available. And that's where the new guest goes. And this actually works. It works because every room has a room to the right of it. Whatever room you're in, there's another room to your right. And if everybody simply moves one room over, nobody gets stuck without a room, but room 1 frees up. And yeah, that's the crux of it. There is no last room. There's no point where it says this is the last room, there's no other rooms left, because it's an infinite number of rooms. So if this is room 10 million, there's got to be a room 10,000,001. So you can do this simple move over one spot, and you're good to go. Yeah, we can do the hotel as one big long corridor just to keep it simple. Alright, so that's a little weird. right? And if we think of this as an infinite set of doors and this is an infinite set of guests, and we have some new guest showing up, which we'll call, S for student, what we're seeing is that, the size of the set of doors, well, we know that's the same as the size of the set of guests because every guest was in a room and so on. But this is also the same as this. The set of guests with one more element added is exactly the same size as the original set of guests. So yeah, we're going Inception here. So one of the funny things about infinite sets is you can add one more element to it, and in some real sense it's the same size. And when we talk about the size of these infinite sets, we're really looking at this one-to-one correspondence. We can put everything in this set. For everything in this set, we can assign one thing from that set, and vice versa. We could do it with the original G, we can do it with a larger G. And so these two actually have the same size. Alright, let's go forward a bit. Oh, we got time, good. Alright, so suppose 5 more guests show up. And you want to fit 5 more people into the hotel. Is that doable? Absolutely. Just have each person move down 5 spots. Oh, we're just getting started. So we could actually fit, 5 new things into this set. And it's still the same size as the original set. Alright, what about a lot? What about, somewhere in the process of these physicists' experiments, everybody got cloned. And for every person who's coming to this party, there's another person. But they're like a mirror image, so they had trouble reading the map, and they're all late. But now, 2 o'clock in the morning, the party's in full swing, the music is great, the food is awesome, and all of a sudden, another infinite group of people show up at the hotel. And they say, we would like a room at the hotel, please. But they say it backwards, right? So we want to fit an infinite number of new people into this hotel. Is that possible? We know we can fit 1 more. We could fit 1,000,000 more. What about an infinite more number of people? Is there any way to do that? And I'll tell you the punchline, yes, there is. You can fit an infinite number of new people into this same hotel. Well, we can't shift an infinite number of rooms to the right because the infinity is not a number, so you can't tell somebody, please move down to the room an infinite number of spots to your right. But that's a reasonable idea. It's just hard to implement. But there is a pretty straightforward way to do this. So the front desk clerk presses a different button and lights up a different sign. And that sign says, pardon the inconvenience. Whatever room number you're in, could you please move to the room with twice that number? So the person in room 1 moves to room 2, the person in room 2 moves to 4, the person in 3 moves to 6, the person in 5 will move to 10, and so on. Now each person only has to move a finite distance. Nobody has to walk forever, right? Each person moves a finite distance. Everybody can find a room, because whatever your room number is, twice that number is still a room. But after this little shuffle, guess what? All of the odd room numbers are available. And now if you're guest N, you can just go to room, I don't know, 2 times n minus 1. So guest 1 goes to room 1, guest 2 goes to room 3, guest 3 goes to room 5. And you can assign a new room to each of these infinite number of new guests. So this is part of the nature of infinities, right? You can have an infinite set, and if you add a few more things to it, it doesn't get any bigger. And if you throw in a whole nother infinite set, it still doesn't get any bigger. And that's a little disturbing, but kind of cool. All right, now comes the weird part. So there's another hotel on the other side of town called Blauman's Hotel. And Blauman was a colleague of David Hilbert. They were kind of like, arch enemies. And Blauman, after Hilbert built his Grand Hotel, Blauman built Blauman's Grander Hotel. And Blauman's Hotel was grander in the following sense. Had an infinite number of rooms, but the door numbers were real numbers. They were all positive real numbers. And let's say they were all less than 100. But any real number you can think of, there was a door with that number on it. And any number between 1 and 100, there was a door with that. Alright, so Blauman's Hotel has, infinite number of rooms, but the door numbers are real numbers. And this hotel is also completely full. Every room has a guest in it, and it's exactly full. And the guests at Blauman's Hotel hear the noise coming from the party at Hilbert's Hotel, and they say, hey, let's go over to Hilbert's Hotel. I've been wanting to check it out anyway. Let's go join the party. And so this infinite number of guests goes over to Hilbert's Hotel, and they say, can you squeeze us in? And the clerk shakes their head and says, sorry, there's no room available for you. And the problem is that this infinite number of rooms is in some fundamental sense bigger than this infinite number of rooms. No, it's a one-night party. It's a really, really good party, though. Someone asked if it goes on an infinite amount of time. Maybe it's still going on. So a hotel where the door numbers are coded with real numbers and every room is occupied is somehow a fundamentally bigger set than this room where the doors are labeled with integers. And so in the language of cardinality in mathematics, what we can write is something like this. The size of the set of reals is bigger than the size of the integers. But it turns out the integers have the same size as the positives, which is also the same size as the negatives, which is also the same size as lots of other sets that we could think of. This is also the same size as the set of fractions. And we can show that another time. And complex numbers with integer coefficients, same size as the integers. Because complex numbers, that's just a pair of numbers, and that's, if we think of integers, fractions are just a pair of integers, right? Something divided by something else. And this would probably feel like it should be bigger than the integers, right? Because this is, the integers crossed with the integers. It's the same cardinality. But the fact is, the real numbers have fundamentally bigger cardinality. And we'll prove this another day. We're going to run out of time here. But we can prove pretty easily that there are fundamentally more real numbers than there are integers, in the sense that it's a bigger version of infinity. And what that means is we cannot find a one-to-one correspondence between integers and reals. Now, a lot of things have the cardinality of the integers, and so we have a symbol for that. And the symbol is called aleph naught. My alephs aren't pretty. If you see this written properly, it's a really cool looking symbol. But aleph naught. And sometimes we say anything with the cardinality of the integers is countable. And it's countable in the sense that if something has the same size as the set of integers, it also has the same size as the set of positive numbers, which means we could number all the things in that set and count them, starting from 1. This is how we can show that the rational numbers have the same cardinality, because we can put an ordering on rational numbers, and then we can count them, right? And if we count high enough, we'll eventually get to any fraction that you can think of. So being countable means you have the same cardinality as the integers, and it means your cardinality is aleph naught. Now, the cardinality of the real numbers is strictly bigger than aleph naught, and that's easy to prove. So here's the interesting question. So question: is there some set, I'll call it X, such that the real numbers have bigger cardinality than X, and X has bigger cardinality than the integers? All right, we know the real numbers are bigger than the integers. We know that rational numbers are the same as the integers. We know that positive numbers are the same, prime numbers are the same, even numbers, odd numbers are the same. The cross product of 5 copies of the integers are the same. But if we keep adding in more and more and more stuff, eventually we jump up to the real numbers, and that's something that's fundamentally bigger. But the question is there some set that's smaller than the reals but bigger than the integers? So is there some set X with cardinality strictly between the reals and the integers? So there's a hypothesis, which is called the continuum hypothesis, or CH, says no. The hypothesis is that if you get a set that is fundamentally bigger than the integers, it's at least as big as the reals. In other words, there's nothing in between the size of the integers and the size of the reals. That's what the continuum hypothesis claims. But it's never been proven. So real quick, chime into chat. Do you think the continuum hypothesis is true or false? Just gut feeling. Do you think that there's nothing between the integers and the reals, or do you think it's possible that there might be some set in between there?
Integers are just whole numbers, right?
Whole numbers, correct.
Maybe if... Yeah, that's very good.
You gotta have a gut feeling one way or another. Doesn't have to be a correct gut feeling. So we got some people saying, I don't know, maybe, or lack the information. We got one, don't think so. And I would say, at least in the past, the majority opinion has been that you know, this is probably true. There is no set in between. Aleph 1 is the smallest set with cardinality bigger than Z. So this basically says, is the cardinality of the reals equal to Aleph 1? Or is there some smaller set that's equal to Aleph 1? So it's a hard question to even sort of imagine how to go about trying to answer it. Now, if you could find such a set, right, it's easy to prove that there is such an X. If there is, you just have to find it, right? So, you know, you look around the bottom of your pencil jar and it's like, oh yeah, hey, check this set out, you know. And you study it and you say, oh yeah, it's bigger than Z, it's smaller than R, you're done. You've proven it, right? But to prove that there is no such set, that's generally a harder problem. So yeah, we don't know, and it's undecided. Nobody has proven this, nobody has found a counterexample. But I'll tell you what has been proven. It has been proven that it is impossible to prove or disprove the continuum hypothesis.
Just like it's impossible to prove or disprove the edge list.
Mm-hmm. Kind of. So think about that. It's a pretty simple statement, right? It took 30 minutes with a lot of addition, additional details, right? But it's a fairly straightforward statement. It's a simple question. Is there a set with size between here and here? Not only don't we know the answer to it, but we've proven that we can never know the answer to it one way or another. We can never prove it, and we can never disprove it. And that has been proven. Yeah, that's sick. So what does that mean? It means we cannot discover a set that lies in between here, because if we did, that would disprove the continuum hypothesis. But we also cannot prove that such a set does not exist, because that would prove the continuum hypothesis. So this is what's called undecidable. And it's been proven that this is undecidable. Yeah, it gets into some interesting quantum stuff, I suspect. So if you want to go down a rabbit hole over the weekend, go ahead and Google Kurt Gödel, G-O-D-E-L. And he did some of the groundbreaking work on undecidable propositions in the early part of the 20th century. And he came up with a paper that he presented at a conference, and almost nobody was in the audience because nobody knew who this person was. He was, you know, an unknown mathematician. But there were a few people who had read his paper and were like, oh my gosh. And they were in the audience to listen to this presentation. And this really changed the face of mathematics, and in some ways philosophy and religion and logic and, you know, our understanding of reality in a very real sense. All right. So that's where we're going to leave things for now. So and like I say, that's not going to be on the exam, but I want you to have at least seen this once, because, you know, it's we're right up at the edge of this with set theory anyway, so it's nice to sort of see the weirdness of it. All right, so that will pretty much do us for set theory. We'll talk about functions on Monday, and then we'll move on to our next topic, which is going to be dealing with propositional logic. So theorems and proofs and ways to prove things, and that will be a sort of central theme for the rest of this course. All right, well, the sun was out a little while ago. It's probably coming back, so hopefully you have a great afternoon, and I will see you next time. Have a good weekend.